All right, let's finish out this lesson on 9.1. Now, the last thing to consider is how do you actually combine roots together that are added and subtracted? Well, it only works under certain conditions. Okay? In order to be able to add and subtract, we need to be able to have two things. You need to have the same index number and the same radicand. So, for example, this is, you need to have the same, oh, let me highlight these. I like this. We'll highlight the index needs to be the same, and the radicand, or what's underneath the symbol, needs to be the same on both of them. If they're not, then you can't actually add them together. And they have to stay as separate pieces. Now, that's not to say that you can't try to make them the same, because our original rules of simplifying still apply. You still want to reduce them as much as possible. You still can't have fractions on the inside of the radicand. And the radicals, there's no radicals in the denominator. So let's look at an example. Here we go. There's two simple rules. Let me look back at it before I go any further. They must have the same index and same radicand, the same on the inside. So when we look here, we're like, okay, do they have the same index? Well, this one's a 4, this one's a 3. Oh, well, one's a 4, one's a 3. So it is already done. There's nothing more to do. Cannot simplify more. That's it. That's as far as you can go. They don't have the same index number. They don't even have the same radicands. So it can't go any further. Let's try another example. Do they have the same indexes? Yeah, look, they've got the same index. They're both a 3. What about the radicands? Well, they're not the same. But could we possibly make them the same? Maybe. The problem is that when we factor tree this one, it becomes 2 times 3, which we would need 3 2s or 3 3s in order to match the index and pull out a whole number. So this is actually as simple as it goes. And 9 goes into 3 and 3. Well, there's 2 repeated, but that doesn't do any good for us because we need it to be 3 total of them. So actually, these are as far as they can go. So done. Cannot simplify more, because they have to follow the rules of the same index and the same radicand. What about here? Well, initially you're like, well, is it really the same? And since the 3 of the index matches this 3 of the index, and the 6 of the radicand matches 6 of the radicand, they are essentially the exact same root. However, how do you actually add them? Well, think of this first one. Let's just temporarily we're going to call 3 cube root 6, we're going to call it x. So this is really x plus 2x. How many x's do you end up with? Well, you end up with 3x. But remember, these aren't really x's, they are the cube root of 6. So our final answer is really 3 cube root of 6. And there it is. In short, as long as the index are the same and the radicands, the arguments on the inside, are the same, then you just add the coefficients. In this case, there's a coefficient of 1 because it's not written. And this is a coefficient of 2. And 1 plus 2 is 3. So you just add the coefficients. But the roots first have to be exactly the same. What about here? Well, let's see. I've got a 5 root 7. It has an index. Well, the index isn't written, so it's a 2. So if I need to, I can put a 2 there. On this one, the index isn't also written, so it's a 2 as well. And same with the last one back here. It's not written, so it's a 2. So all the indexes are the same. Yay! But not all of the inside pieces are the same. This is a 7, this is an 11, but this is a 7. In order to add and subtract them, the radicands, the inside piece, and the index have to be exactly the same. So in this case, I have some that do combined, but not all of them do. There is no other 11, so my final answer is just going to have the square root of 11. But what about the others? This first one and last one are the same. Now it just becomes 5 minus 8, which is a negative 3 square root 7. So you only, if you can add them, you just add the ones that actually go together. You might think of back when we were doing earlier stuff with polynomials, if you have x cubed plus 2x squared plus 9x to the fourth plus 3x squared, the only ones that actually can go together are the ones that are the same. If they're not the same, they don't go together. Same thing here. If they are not the same, they don't go together. Let's do another one. Well, what do we got here? Okay, well, I have 10 cube root of 10. Okay, and then a cube root of 40. Now, yes, the cube root is the same, but the inside pieces are not the same. Could I make them the same? Maybe. That's when we have the factor tree. 10, it can be factored into 2 times 5, which isn't very helpful because there's only 1 2 and 1 5. We would need 3 2s or 3 5s in order to satisfy the index and pull a whole number out. So that one's not going to simplify any further. What about the 40? Well, let's see. 40 would simplify into, 4 times 10. And 4 breaks into, a 2 times a 2. And a 10 breaks into a 2 times a 5. Oh, hey, look at that. I have 3 2s. Which means the cube root of 40 could actually be I'm going to write the first stuff. The cube root of 40 can actually be written as 2 times 2 times 2 times 5. Which then we could say, well, these could be written, all 3 of them could be written as, 2 cubed, then times 5. And then my exponent matches my index, and so my whole number could come out. I would get an answer like this. I still have my 10 cube root of 10, but then I have a 2 that comes out. So it would be 2, and then I didn't take out the 5, so it's cube root 5. Now are they the same? No, they're closer. This, though, is still a 10, and this is still a 5. So I'm done. That's as far as it goes. I satisfied the rules of I had to reduce it, which we reduced the 40 down to a 2 root, cube root 5. So we still satisfied it. We still reduced it. But in the end, they still did not combine. Let's do another one. Here we go. 6 fifth root of x plus 2 fifth root of x. Well, is the fifth root of x the same as the fifth root of x? Well, yes, they are. So now I just get to add the coefficients. 6 plus 2, which means I have 8 fifth roots of x. And no simplifying to do any further. Again, I'm trying to highlight the idea that they will not add or subtract unless the index and the radicand are exactly the same. Now, we're going to spend most of our time with square roots. We won't really do cube roots, and we definitely will not really mess with fifth roots, but the rules still work the same. Let me do one more here. I have a square root of 2, a square root of 2, and a square root of 2. They are all exactly the same radicands. They are all exactly the same index. So now I just get to mess with the numbers up front. What is 9 minus 14? Because you can think of this as 9x minus 14x plus 2x. Well, 9 minus 14 is negative 5. Plus 2 means it ends up as a negative 3x, or negative 3 root 2. There we go. Now I'm just going to jump down to this one here. I'm going to jump to 10. We've seen these before where we distribute. But this will be our final example of combining. I'm going to start by doing my distributing property. I'm going to distribute root 5 times root 3. Then I have root 5 times negative root 7, d5. There we go. So now I can do the math. We've learned previously that if two roots are multiplied together, you can write them under a single root. 5 times 75. I'm sure I could do that in my head, but there we go. 375. Woo! And I probably should have just combined those two and to make 15. So now I got to figure out, can I reduce this any further? Because 15 only breaks down into 5 and 3. Definitely no whole numbers to pull out. But does 375 break down to anything I can pull out? Well, let's see. 375, well, I know it divides by 5 because I had to multiply it by 5. Let's see, what else could we do? Let's go 375. Because this one's a 15 and I want to know if they can add together, they both need to be a 15. Let's see if it divides by 15. Ooh, it does. So then I get the square root of 15 minus the square root of, well, let's see, 15 times 25. There we go. So I just kind of rewrote it. Let's break this into two roots because I happen to know the square root of 25 and hopefully you do as well. We got the square root of 15 minus the square root of 15 times the square root of 25, and the square root of 25 we should know. It's 5. So I have root 15 minus 5 roots of 15 because this itself is 5. And we typically write the whole number in front of the root symbol, like we did here. So now what is 1 root square root 15 minus 5 square root 15? Basically, I'm asking what's 1 minus 5? Well, it's negative 4 square roots of 15. So don't forget that after you distribute, or maybe even before you distribute, you might need to simplify it to see if it'll actually combine. All right, there you go. That is how you add and subtract roots. That finishes out 9.1.